I know it's time for coffee, but I already thank you for being patient and sitting here. So, hi, I am Vikas Sharma. I am a fourth year PhD student working with Dr. Orko Banerjee at ISER Pune. The topic of my current project is N-body simulations for LiMR cosmology. I'll start with a brief motivation to the topic. As everyone in the room knows that more than 80 to 85% of the matter in our universe is made up of something which we very feebly understand. We call it dark matter. Now there are different models of what this dark matter could be. It could be some cold dark matter particle. It could be some hot dark matter particle. There might be some ultralight dark matter species, or there can also be some self interaction within these dark matter particles, or it can be something else that no one of us has thought of yet. But as we know from the standard model that there exist a number of species for the baryonic part of the universe, similarly there is no reason to assume that all the dark sector has to be made up of only one kind of particle. So we assume a scenario where you have although there are theoretical reasons to assume that majority of the dark matter has to be made up of cold dark matter. So we consider a scenario where CDM is still the dominant part of the total matter density in the universe, but you also have another species which is a light species. So there is a group of particles which people have termed recently as LiMRs. LiMR stands for light but massive relics. So these particles being of the order of, so their mass is of the order of a few electron volts. So these particles act like hot dark matter species, and being very light, they would show up in the as a change in delta n effective value at the CMB, because they are relativistic. The significant part of them is relativistic at the CMB, and then they would become non-relativistic at late times and will add to the structure formation today. Now people have tried to put constraint on properties of these LiMR particles, but no one has explored the full non-linear regime. There have been studies on the linear scales. Now we want to use N-body simulations to explore the complete non-linear regime. Now let me tell you what the methodology previous to this work exists. So to run an N-body simulation, this is a way. So you start with class. I think class needs no introduction in this community. And then there is a code called reps, which is scaled for rescaled power spectrum. So when you want to run, when you want to set up the initial condition for a massive neutrino cosmology, if you directly start with class and then run N-body simulations, you will face some discrepancies. So reps modifies class's power spectrum at initial redshift. In our case, we choose it to be 99, and sets up the initial condition to run a massive neutrino simulation. And then we have engine IC, which comes up with the gadget. So what engine IC does is it takes the initial power spectrum from reps and then sets up the initial particle position and velocities in a simulation box, and then gadget runs the N-body simulation. Now this pipeline already works for a scenario when you have only CDM and CDM with massive neutrinos. We want to modify it to a scenario where this pipeline works for a 3-fluid scenario. By 3-fluid I mean you have CDM particle, standard model neutrinos, and these third species of LiMR particles. That is what we want to do. So for doing that, the plan is we first will have to modify reps to set up the initial condition for a 3-fluid case. Then we would have to modify engine IC to again for a 3-fluid scenario, and then we will have to modify gadget. Now we start with taking inspiration from reps so reps solves the fluid equations for doing the backscaling on the classes power spectrum. So these are a set of continuity and Euler equation for CDM and neutrino particles. We assume baryons to be pressureless for our case. And then we also set up the equation for LiMR particles similarly to that of neutrinos, apart from the difference that they would have a different free streaming scale apart from the neutrino particles. And when then we close this set of equation with the Poisson equation. We consider these normalizations and solve the set of equation that I showed on the previous slide. The point to note is that these existence of these LiMR species will change the growth rates of CDM as well as the neutrino particles. Now before going to the results, I would like to show you some checks that we had to do on the 3-fluid pipeline. So if you remember, the first point was to modify reps. So we write a code called pyreps. Reps was originally written in C. Pyreps is written in Python, hence the name pyreps. Uh, we said we so the pyreps is capable of running setting up the initial condition for a 3 fluid scenario, but before running it for a 3 fluid case, we should check it for a 1 fluid and 2 fluid against reps, so that we know that the code is working fine. These results show exactly that, and the result between reps and pyreps match within the machine precision. Pyreps is now a publicly available code. You can scan this QR to for the GitHub page, and then pyreps is done. So my modification to reps is done. Next step is to modify engine IC. Now a perfect check to see if engine IC is working fine or not is, so what engine IC does is it takes the power spectrum, sets up the initial particles, position and velocities. Now from that box of initial particles, you read density field, generate the power spectrum. Now the power spectrum thus generated should match with the power spectrum you fed it with, and that is what exactly this plot shows. So engine IC is also done. This also works. Now the next step would be to modify gadget. We do that, and now we have the complete pipeline. Here is a final check before running, showing the final results. Consider these two scenarios. In one case, you have a CDM particle and 3 neutrino species. In other case, you have a CDM particle and 2 neutrinos and a third LiMR particle. These are initial conditions at 99. You pass it through the pipeline that we had just set up, and you get the results at redshift 0. Now, if you consider that this LiMR particle is a neutrino, then the scenario would be, in one case you have a CDM particle with 3 neutrinos, in other case you have a CDM particle, 2 neutrinos and the third neutrino is passed with the LiMR flag. In principle, these two scenarios are same. Now, the result should match if the pipeline is working correct. These are the results where you see that both at redshift of 99 and at redshift of 0, we are able to match the results, hence the pipeline is working fine. Now I will show you the results. Before showing you some quantitative results, I would like to show you qualitatively how the structure formation is, structure is washed out due to the presence of these LiMR particles. So in this video, in this video, you can see for the first case where I have only CDM particle, here CDM with standard model neutrinos, and in this case we have all the 3 species. And if you cannot notice, then I also have the zoomed in picture for you. So this is the only CDM case, this is 2 fluid CDM plus standard model neutrinos, and this is a 3 fluid case, and this box has been zoomed in on the lower panel. One can see that as you include standard model neutrinos and LiMRs further, the structure is washed out. Now if you look at the individual clustering of these particles, CDM clusters the most, of course. Neutrinos have very less clustering, and LiMRs have clustering somewhere much more than neutrinos, but still less than the CDM, which is expected. Now I will show you some results. So we choose the LiMR particle to be a Dirac fermion in the first case, and then we produce the power spectrum. So here you can see the power spectrum of only CDM case, CDM along with neutrino, standard model neutrino case, and the following is what I will follow in the next plots also. We do 2 things. First, we keep temperature of the LiMR particle fixed and vary mass of the LiMR particle. In other case, we keep mass of the LiMR particle fixed and vary temperature. One can see that suppression is more when you increase the mass of LiMR particle, which is expected, and here you can see that as you increase the temperature of the LiMR particle, the suppression is more. So this is for the power spectrum. Then we go on and look at the halo mass function. Halo mass function is defines how number density of halos would change with mass of the halo in the simulation box, and we also see the suppression here in the similar manner as we saw for the power spectrum. One thing to note for the halo mass function is, so to produce the halo catalog, we use code called rockstar. Now rockstar is only sensitive to the type 1 particle, which means that contribution from standard model neutrinos and the LiMR particles has not been considered in this case. So these are comparison between only CDM halo mass functions for different scenarios. Then we go go on and look at the mass concentration relation between halos. So mass concentration relation is defined as the ratio of virial radius with the scale radius. Qualitatively, it tells you how centrally peaked the density profile of a dark matter halo is. So we also in this case also the contribution from the other two species has not been taken into account. These are only CDM comparisons, and trends are as expected. For low mass halo you have higher concentration, for high mass halo you have lower concentration, which is expected. And then we go on and calculate weak lensing. Now to calculate weak lensing in a simulation box, we calculate something called excess surface mass density. Now excess surface mass density is calculated as this quantity, and here in this case we take into account the contribution from all the three particles, and then we add the weak lensing signal in all the three cases. The trends are as expected in that case. Now one thing to note in all the plots is that the power spectrum of all the observables are more sensitive to the temperature as compared to the mass, and that is what we expect, because the things are more sensitive when you change temperature. And then we go on and look at like instead, so in the previous case we had considered a fermionic species for the LiMR particle. We also go on and consider LiMR to be a boson. We change the distribution function while setting up their velocities, and we again calculate all the four things that we had calculated: power spectrum, halo mass function, concentration, and weak lensing. So I'll not go into the details. The trends are similar to what we had for a fermionic species. And so these are the first results from n-body simulation of three fluids evolving non-linearly, fully non-linearly. Now these are the very first results, and there are a lot of things to explore. For the current work we had only thermal LiMRs. We also want to look at how non-thermal LiMRs would evolve. Then we also want to look at if the thermal velocities of these velocities of these LiMR particles might have some other distributions. They might follow Fermi-Dirac or boson that we had checked. They might also follow some other different kind of distribution. We also want to check that, and we also want to we plan to look at how varying free streaming scales and delta N effective value of these for these LiMR particles would change things. These are some references, and thank you for being patient.
Thank you very much. It's very exactly on time. Yeah. Questions?
I have two very naive questions. First of all, as you have seen, you have also seen in your simulations that if you introduce a light dark matter, then the structure starts to wash out, right? So my question is, how much the fraction of dark matter, so maximally it has to be cold dark matter. So what is the fraction of hot dark matter that you can introduce so that you are still okay with the structure formation?
Okay, so these are the first checks. We have not been sensitive to what percentage of the matter you can give it to these LiMR species. That will be constrained once we compare it to the observation. But for now, these are subdominant part of the matter only. They only contribute to a few percentage of the total omega m.
Okay.
Yeah.
And the other thing is that how different it is from dark radiation. So people often talk about dark radiations in the.
So these particles at CMB would contribute to dark radiation in the sense that they would have a non-zero delta N effective value.
Yes.
But at late times, due to their massiveness, late time somewhere between CMB and today, they would become non-relativistic and then start contributing to the large-scale structure formation.
Okay.
Yeah.
Thank you.
Hi, Vikhya. Thanks for a nice talk. I'm just curious about one thing. You said Dirac fermions. Where
Yes.
does the Diracness nature come in? If I do it for Majorana fermions, it should be the same, right?
Okay, so if you change the what you call G value for the species,
Yes.
that value is highly sensitive to the value of delta N effective that you will have. And
Yes.
when you calculate the omega, which is the contribution of these particles in the omega matter, that is also sensitive to that G value. So G value is different for Majorana and Dirac. So that is why I said that we have chosen Dirac.
Okay.
Yes,
Thank
because
you.
that is sensitive to those two.
Thanks very much for the nice talk. Thanks.